I work for Epic Games now, but this has nothing to do with Epic. I did this library when I was working at Google, and we were developing a chip for machine learning. And if you've ever looked into machine learning, you know that it's all about manipulating arrays, or they often like to call them tensors, but they're really multidimensional arrays. So first, the name Orthotope. So I mean, I wanted to call it array, but that's of course taken. There's already a library called array. And I wanted to call it tensor, but there's already a library called tensor. So I looked for some other word. And orthotope is the generalization of a rectangle to higher dimension. So I picked that name. It's a terrible name because I can't remember it myself. I'm serious. I've had to look it up, to do some search to remember what it was. Okay, a few words about APL before I get into this library. So it's an array-based language designed in the 1960s by Ken Iverson. It's much ahead of its time, I would say. It's a very functional language. It has assignments too, but I view those assignments more as a sign that they forgot to have some kind of let expressions in APL. So you need something, need to be able to name intermediate things. If you've heard anything about APL, you've probably heard that it's a cryptic language, very short. So I have an example here of an APL program that computes prime numbers up to some number r. Don't ask me to explain it. So I think APL never got popular because it, as you can see here, it uses all these symbols that you don't have on ordinary keyboards. So you had to have a special APL keyboard to be able to use APL. And well, IBM sold the little machines that had special APL keyboards, but it never really caught on. But it has all kinds of cool sort of high-level features that you never loop around things. You do everything in sort of bulk operations, which I'm going to illustrate with some of these things that I have. Yes, Orthotope, it's a Haskell library, and mostly it provides structural operations. And what do I mean by that? I mean things that don't really touch the elements of the array. You just rearrange the elements of the array. So transposing a matrix is an example of this. You don't really care what the values are in the matrix. You're just switching the two axes around. And there are lots of those. And a lot of those operations can be done in constant time with the way I represent arrays. And I'm going to show you some examples. I'm not going to go through the complete API. And the reason I have mostly these structural things, that if you've done machine learning things, try to code up some neural nets, you know that it's array manipulations everywhere. So you basically only need these structural operations and matrix multiplication. And so Orthotope doesn't contain matrix multiplication. You can easily code up matrix multiplication, but if you want it to be fast, there is another library that comes sort of as a companion called matrix, which uses the H-matrix library in Haskell, which in turn uses LAPACK and BLAS, and so you get really fast matrix multiply through that. Okay, so just to show you what the notation I'm going to use. So arrays will be displayed in my examples in the same way as they are displayed in APL. So in the top left corner there, it says 1, 2, 3, 4, 5, 6 on 2 different lines. So that means it's a 2 by 3 array. So the innermost dimension is always displayed on a line, and then the next dimension is displayed on subsequent lines. And if you have even more, like the bottom left, 2, 2, 3, then there is a blank line in between the sort of the first and the second element in the next dimension. And then if you have even more dimensions, there are even more blank lines. And the dimensions of the array is usually called the shape. So the 1, 2, 3, 4, 5, 6 has shape 2, 3, and the next one you can see there's shape 3, 2. A vector has shape 3 there with 3 elements. But you can also, I mean, there are many things that look like that when you display them. So if you have something of shape 1, 3, so it says it has 1 in the outermost dimension, that looks the same when you look at it as something that just had 3 elements. And 3, 1 you can see there. And the rank of an array is the number of dimensions that it has, so it's the length of the shape. And the size we're not really going to use, that's mostly uninteresting. A couple of interesting special cases. So, I mean, you can have an array, a one-dimensional array with 1 element in it, and that has, of course, 1 element. You could also have a 0-dimensional array, which will have 1 element in it too. So you might wonder, why does a 0-dimensional array have an element in it? Well, if you think of the number of elements you have, it's really the product of all the numbers in the shape. So if it has shape 2, 2, 1, 3, if you multiply those together, you get 12. That's the number of elements you have in it. And if you, in Haskell, take the product of the empty list, you'll get 1. So 1 is the natural thing to have for a 0-dimensional array. Oh, by the way, I forgot to say, if you have any questions, please interrupt me, wave your arms or something, and I will try to see you. Yes? Depends on what you mean by scalars. So in APL, they're often called scalars, these things that are just, but it's sort of confusingly called scalars because they're also the atomic values that are just, there's a 1, there is a real 1, and then there's also the 0-dimensional array that contains a 1. And for most things in APL, you always stay in the array world, so you never get out of it. It's always an array. So you really can't get out of the arrays. So you can kind of call them scalars. Yes, so when I did this, I tried to make a library that is strongly typed so that the shape of the array is part of the type. So this requires a number of Haskell extensions, of course, because you need numbers in the types. But you can see a few here. So an array 2, 3 of int is a 2 by 3 array of integers. Array 6, a 6-element. Array 4, 4, 4, 4 bool is a 256 sized array of booleans. Let's see, do I mention here on? No, let me just briefly say, I'll come back to it. This is very neat when it works, and if you have numbers, it works very well. But if you try to do some more advanced things where you need algebra rather than arithmetic, then you get horrible constraints. I, of course, have borrowed the stuff from Clash that simplifies these kind of constraints, but it's not enough because that deals with numbers, and this also, these shapes, there really needs to be a simplifier for shapes, because shapes have an algebra too. But in my examples, I'm going to stick with these. But there are actually 3 versions of the API. There's this one that has the shape as part of the type. There is one that's a little less strongly typed, that only has the rank as part of the type. And then there's the one that has nothing as part of the type, so it just says array int, and everything is checked at runtime. Okay, so is this readable? Yeah, I wonder if I can, it's hard to, I shouldn't have used this, this special background that, if this was a normal computer here, I could go in and remove the background, but I don't know how to do that here. So you'll have to suffer, I'm sorry. So on the first line there, it says A equals from list 1.6. And from list is a function that takes a list of numbers and produces an array. What shape does the array have? Well, from list doesn't know. So you can give it a type annotation saying array 2,3 int, and then you get something. And if you pretty print it, you get 1, 2, 3, 4, 5, 6. And you can see there that the type of from list, well, it takes in a list of elements and you get an array of some shape. You could also give the shape. So this, if you program with this version of the library where you use the explicit dimensions as part of the types, you use this type application feature of Haskell a lot, because you need to often pass in some information about what the shape or the dimensions are. So you can say from list at 2,3, which means the first argument to from list, which is the sh, the shape is 2,3, and you get the same thing. And this is, of course, checked at runtime. There's no way it can know that I'm giving it an array of, or a list of 6 elements. So if I want a shape with 6 things in it, it had better check that. Yeah, shape, rank, the size of it, and iota is a popular function in APL. So it gives you a vector of the number of elements you need. So if you're in the strongly typed one, you don't always have to say anything. Here I couldn't figure out how big it was supposed to be, but sometimes type inference helps you. So you can just say iota, and you get 0 up to something. So APL is a bit schizophrenic, by the way. So if you ever use APL, you might get the list 1 up to 10 instead of 0 up to 9. But then there's usually a global switch you can set in the system if you want 0 or 1 based indexing. So I don't know how they can do anything with that, because that seems terrible. Yes, indexing. So A is the same as on the previous slide. So you can index in A with 1. I have 0-based indexing. So when you index, you get a new array, a subarray. So you remove the outermost dimension and pick out only one of the subarrays from the outermost dimension. So you can see here 4, 5, 6 is the thing you get. And then you can index in that again with 0, and then you get the 4. And that 4 is still an array. It's you've sliced off one more dimension, so it's a 0-dimensional array. And you can see for the type of index that it takes an array that has some size and a shape, and you get an array where it's taken off one thing from the dimension. This is dynamically checked again. I had one version of this where you also had numbers that were strongly typed, so you know how big they were. No. So this is not APL, so I actually have a function called unscalar, which takes one of these zero-dimensional things and picks out the thing inside it. As far as I know, APL doesn't really have that. You're stuck. Transpose is a popular thing to do. So you have a matrix and you want to sort of mirror image it across the diagonal. So 1, 2, is it still working? Yeah, okay. 1, 2, 3 turns into this other one, 1, 4, 2, 5, 3, 6. So you might wonder why is there an extra argument there to transpose? Well, if you have a two-dimensional thing, you know what you want to do with transpose. You want to switch the two axes around. But say that you have 4 dimensions. What does transpose mean then? Well, you can rearrange the axis in all kinds of ways. And so you have to give the permutation of the axis as the first argument. And if I try to transpose here, say 2, 0, you get some incomprehensible error message, which is typical for this kind of type-level programming. I guess I didn't show the type of transpose. Anyway, the type of transpose, if you look at that, it says that that first argument actually has to be a permutation of the numbers of the axis. So it checks that you're not doing anything too weird. Yeah, this is just more transpose. Or maybe I have the type. Yes, here is the type. This is the type of transpose. Takes an array with some shape, produces a new array where it has permuted the shape by is. So is is this first argument, and this permute will fail at compile time if it's not a permutation. But it checks here that the rank, so the number of elements in is smaller or equal to the rank of the shape. So you can permute just some initial part of the axis if you want to. Yeah, so these kind of types, horrible as they are, they show up a lot. So I have to confess that when I use this for sort of experimentation, I always use the version that is dynamically type-checked. And then if I sort of wanted to put it on more solid footing, I might go through the pain of doing this kind of thing. Reshape is a very popular operation with in APL. So it says, take my array that has some number of elements and just interpret it as some different array with the same number of elements, but with some other dimensions. So the product of all the dimensions have to be the same in the two. So, well, the old A we had before that had 1, 2, 3, 4, 5, 6. I can say, oh, just take the elements and think of it as a 3x2 matrix. So this is not transposition. This is just the elements come in the same order. It's just that they are interpreted as a different shape. So it's 1, 2, 3, 4, 5, 6. And here, take iota and reshape it into 3, 3, 3. And so, well, here it could figure out how many elements you needed. You need 27 for this to work. And so you can see that it's given you 3 by 3 by 3. And reshape, the type is not too bad. The input and output shapes, they have to be shapes, and the sizes of them have to be the same. I made changes to my slides about an hour ago. Those changes are not here. Oh well. Let's skip this slide. No, that who knows what could happen. I will improvise. Yeah, there's a point where there should be another slide. I forgot to tell you what's bad about this array library. So there won't be a slide about that now. There will only be words that you will forget. There is some arithmetic you can do on these if you want to. So you can say a plus a, so that means pointwise or Hadamard operation. So you add them. So it's the same 1, 2, 3, 4, 5, 6 that is a still. Or you can add just a 1, and 1 will then sort of get promoted up to being an array as well. Or you can take the square root. So here I'm just illustrating this function called broadcast, which is in APL, it's kind of automatic. In this library, you have to do it yourself. So it takes an array, this C array you see has 100 and 1,000 in it. And now I said, I want to broadcast it. I want to make a bigger array where you replicate the 100 and 1,000 as many times as is needed. And it has an argument saying that axis 0 in the input goes into axis 0 in the output. But we need an axis 1 because A is two-dimensional. So it will just replicate. So that's why you have 101, 102, 103, 1004, 1005, 1006, because it's been replicating the 100 3 times and 1,000 3 times to make it the same size. Another operation that actually does something with the elements, I said there were not too many of these, is reduce. This takes, it's like fold. It takes a function and some starting element, and it combines them all with that. And, you can see the type. And it gives you a zero-dimensional array back. So you might say, that's kind of a useless function because that reduces the entire array. What if I just wanted to reduce some part of it and not all of it? Well, this is one of the cool things about APL. There's this thing called re-rank, which means if you have something that operates on a whole array, you can say, I don't want it to operate on the whole array. I want to look down some number of levels and just operate on those subarrays. So here I say re-rank 1 sum. So that means don't operate on the whole array A. Instead, go 1 dimension down and use sum on all those subarrays. And so if you go 1 dimension down and sum, then you sum up 1, 2, 3, and you sum up 4, 5, 6, and you get 6, 15. And then you might say, yeah, okay, that's good, but what if I wanted to sum on the other dimension and not sort of go down 1? Well, then you can transpose. You transpose the thing into the sort of the top one into the bottom one, and then you re-rank, and then you sum those, and then you get 5, 7, 9. So using re-rank and transpose, you can sort of creatively make functions that sort of operate on any sub-piece of the array that you want to do your, in this case, summation on. And this, yeah.
Okay, so in the first example, I see that it doesn't keep the shape, so to speak, so it isn't 6 and 13 under it, right?
No, it's sort of let's back up. Reduce takes an array of any shape and gives you a zero-dimensional array back. And so when you've re-ranked it 1 step down, the dimension you kept, that will still be there in the end, but everything under will have turned into a zero-dimensional array, and sort of that's all squashed together. So that's why you get 16. The outermost dimension here is 2, so you get to keep 2. And then, of course, when it's displayed, it's sort of the innermost dimension, which is the only one here, is always displayed this way. So it might look a little confusing that it's not that way, but it's because one dimension has disappeared.
Thank you.
So I thought I'd show you how you can do matrix multiply, and if you have forgotten how to do matrix multiply, here are a couple of matrices. So to produce the top left result, you take the top row and the leftmost column, and you fold the column down, and then you multiply them element-wise, and then you add all that up. So that's 1 times 11, 2 times 13, 3 times 15, and you add them up, you get 82. And then you do the same thing. You move a column over, and then you get 88, and so on. So how can we do this using the operations that we have? Well, here are the two matrices, 1, 2, 3, 4, 5, 6, and the 11, 12, 13, 14, 15, 16, as I had here. We start by transposing B so that you'll see why. I guess this is pretty much unreadable. Yeah, especially the top line. I can't read it myself. So what the first one has done a broadcast of the A array. So you have broadcast the innermost dimension. So now it says 1, 2, 3, 1, 2, 3, 6, 4, 5, 6. Because we're going to need every row several times. And then for the other one, the B, we broadcast the other dimension, not the innermost. So that says 11, 13, 15, 12, 14, 16, and 11, 13, 15, so on again. So now, if you imagine these two and you sort of put them side by side, you can see that the 1, 2, 3 will match up with 11, 13, 15, and then the 1, 2, 3 will match up with 12, 14, 16, and so on. So you can just say, okay, multiply these two, and you'll get all these things that are multiplied. And then we need to sum on the innermost dimension now. That's what we were supposed to do. And so we take the sum function and we re-rank it down. We have a three-dimensional thing now, so we need to re-rank it down twice. And then we get the result of the matrix multiply. So this is one way of doing it. So in APL, matrix multiply is built in, of course. And as I said, in Orthotope, you can download an extra library to get matrix multiply. But as an example of something you can do, yes, the type is actually kind of nice. It's what you want it to be for this simple 2D matrix multiply. An array of size m, n multiplied with the size n, o gives you an array of size m, o. And there it is. Let's see what time we have. I'll skip 1D convolutions in the so I have a few minutes to say something about complexity and the implementation. So as I briefly mentioned before, a lot of these operations are actually constant time, and this was, it's not a new idea. It's using something called dope vectors, which I will show you in just a moment. That was invented in the 60s, and they're also used in some early APL implementation. So dope vectors are independent of APL, but APL used this representation in some implementation I think is from the 60s, possibly the 70s. So there's a bunch of operations that are constant time, like transposition, windowing that you need for convolution. Stride, it means you don't take every element, you take, say, every other element or something from an array. Slice, you want to pick out the subpart of the array. Reverse all the elements along an axis, do indexing. So those are constant time. I might have forgotten some. Then there are some that, if you're lucky, they're constant time. If you're unlucky, they'll take linear time because you need to copy all the elements. And then, of course, as soon as you start operating on the element, it will take the time, the number of elements you have. Yes, this is what I mentioned earlier, that there are 3 versions. There are shaped ones, ranked ones, and dynamic ones. So shape is the one I showed. So shape is part, rank only has the rank of the array as part of the type, and dynamic is dynamic type checking. If it only ended there, so how do you want to store these? Well, unboxed things are nice, but they don't always work. So there are regular boxed things where it uses data.vector to store them. You can have unboxed things where it uses data vector unboxed. But then if you want to talk to C code like a matrix multiply, that data vector unboxed is not good because those arrays are garbage collected. They can move around, so you need them pinned in memory. Then there's data vector storable that gives you pinned arrays that you need to use together with the H-matrix library. And then, since I already had a bunch of different ones, I decided, okay, I'll also provide one where you can give it your own storage. You only have to implement the type class that has certain operations, and you can use any kind of sort of backing store for the arrays. So because the arrays are only a thin layer on top of some kind of vector type. So if you want to do symbolic manipulations, you can do a backend that doesn't actually have any arrays at all. They just sort of do symbolic operations. So that means the API has 3 different kind of types, 4 different kinds of storage. There are 12 variations of this library, so you have to decide which one you want to use. And not only that, there are 12 files that look almost the same. I see this as a flaw in the abstraction power of Haskell. Backpack could have solved a few of those. Okay, I won't move that arm. But I don't see how you can, in Haskell, make something that's generic in the type so that you sometimes can have the shape as part of the type and sometimes not. So it's just a pain. Okay, what about the implementation? So this is the stuff that is in an array. So for each dimension, it stores a size. And for each dimension, it stores a step that tells you how far to move in the vector. There is also a vector to get from one element to the next element in this dimension. A general offset that sort of points somewhere in the vector, and then there's a vector, and the vector holds the actual elements. And so if you want to index with a bunch of indices, you multiply each index by its step size, add the offset, and that is sort of the index into the whole vector of where your element is. So, our old friend 1, 2, 3, 4, 5, 6. So the vector contains just those in order, and the sizes say, well, outermost dimension is 2, innermost is 3. In the outermost, you need to move 3 elements forward to get to the next one. So to get from 1 to 4, you need to move 3 elements. And to get from something in the innermost, you only take 1 step. And the offset is 0. It's not used here. Here's a constant matrix that is 3 by 4, all 7s. Well, you just say the step size is 0 in both dimensions. And so you only need a single 7. And the same thing happens with these, say, broadcast operations that duplicate some dimension. It doesn't change the vector at all. It just fiddles a little bit with these step sizes and makes some of them 0 so that you don't move when you try to step in that index. Transpose, what does transpose do? Well, our old friend here again. Transposing just say, okay, we want to treat the axis the other way around, so you swap the two sizes and you swap the two steps, and then you have the transpose. Oh, it shouldn't say, the offset shouldn't be 1, the offset should be 0 in the second one too, that's a typo. A slice, well, if you want to say a 2x2 slice of that matrix up there, that is the 2, 3, 5, 6 part, you adjust the sizes and you say, okay, I need offset 1 now, because you need to start one element in. So taking a slice of a matrix is also, I call it order 1, because it's just manipulating the number of the sizes and the steps for the dimensions. So all operations that can be expressed as an affine transformation on indices can be done in constant time. And an affine transformation is something that is basically A times I plus B, where I is the indices you have, so it's a vector because it's multidimensional. A tells you how to transform it, and B is some kind of offset. And this works out because this is matrix multiplication, and matrix multiplication is associative, so you can rearrange these. So you can always get down to this normal form of this kind. Okay, so here's the missing slide. So what's bad about this? Well, as you might have guessed, you can easily lose locality here. Things that you, when you look at it, think are as elements that are next to each other, like after you've done a transpose, and you see, oh, that's next to that. Not at all next to each other, because you've taken some large step that the step size told you to take. So if you want to take that and, I don't know, do a matrix multiply or something, you will be jumping all over the place. And sometimes, so if you, for instance, want to pass one of these arrays to a C library, the C library doesn't know about this fancy representation. It thinks that everything is in a long vector, which means you have to copy all the elements into a vector. So there is a bunch of copying going on when you, well, I mean, the API tells you where these things might happen, but it's not perfect. But it's nice that you can do some of them in fairly quickly. It's the library is on Haskell, so you can use it if you want to. And the reason I did it, as I mentioned, was to do some neural net stuff. And you can do, together with matrix multiply, you can do some reasonably efficient. It was one of the edits I made. It says can be used for efficient implementation. I added reasonably efficient because it's not that efficient. All right, that's it.
Great. Thank you very much, Lennart, for that. Do we have any questions from our virtual audience? No?
No.
Any questions in the room? We've got about 5 minutes.
If we interpret multidimensional arrays as arrays of arrays, isn't re-rank equivalent to map?
Yes, kind of. So there is an operation in APL and in the library called ravel, which takes an array and gives you an array of arrays. So if you want to do a re-rank, you could take, you can ravel, and you get an array containing arrays, and then you can map your operation over those subarrays. That's one way of doing re-rank, yes. And then there's the opposite of that in the library is called unravel, which is a little bit, unfortunately, because in English, ravel and unravel mean the same thing.
Couple more questions.
So you said that you started, or usually when you're doing prototyping, you start with the untyped version, and then you go to the typed version. Did you ever get any type errors when you switched? As in, were there any mistakes that were caught
I
then by the
think
typing?
so. Yes, I mean, I probably weeded out the type errors, but there were things I didn't think of, invariants I didn't think of, like, oh yeah, the rank of this thing really always should be less than that. That sort of if I did it wrong, I would get the runtime error, but it's doing it in the strongly typed way sort of gives you more insight to some things, how they have to behave, and especially when you do really complicated things like, I don't know, convolutions or something like that, where there are lots of constraints on sizes that are not obvious.
Okay.
You mentioned that it is reasonably efficient. Have you run any benchmarks compared to state-of-the-art other implementations?
I ran some stuff when I was still at Google, but I unfortunately I don't have any numbers of that. So, but a lot of neural nets is multiplying large matrices. And once you're multiplying large matrices, it will take time. Even the time it takes to copy these is not very significant compared to the time to do the matrix multiply.
Have you thought about combining this with automatic differentiation at all?
I haven't, but it probably combines fairly straightforwardly, because you can have in the boxed version, you can have any numeric type. So I think it would just work.
I think we've got a couple more minutes. Are there any more questions? Oh, one more.
Thanks for the talk. Are there any interesting concrete business applications that you've applied Orthotope to?
No.
Great answer. Thank you.
Any more questions? We've got about a minute left, I think. No? Well, thank you very much. And can we have another warm round of applause for Lennart?
Thank you.